In this section, we're going to introduce the concept of potential energy. And one way to think of potential energy is as a way of storing work. Now, in some sense, we've been calculating potential energy already because potential energy is just another way of looking at the work done. So let's imagine that we've got the Earth and the ball. Now, these aren't to scale, so assume that we can use the Near-Earth Approximation here. So if I define this as my system and this as my surroundings, then there's a net force on the ball in the downward direction, and I can, if this thing moves through a distance delta y, I can calculate the work done, which is just F dot delta R, which in this case just reduces down to, let's see, the net force is a negative mg. The y component is in the negative y direction times delta y. So this is the work done by the surroundings on the Earth. Now, if instead we consider the Earth to be part of the system. Now you remember when we were talking about momentum that we found by putting things inside the system, then the force of interaction between two objects is no longer acting on the system. In other words, because of third law pairs, when both objects are inside the system, those forces essentially cancel. And so in this case, we have that the net force on the system is 0. But how do we account for the interaction between these two? Because clearly the kinetic energy of this ball is going to be increasing. Well, the way we do that is we define potential energy. We'll use the letter U. And potential energy is just going to be mg delta y. Notice that the sign is opposite it was here. By moving this inside the system, we now have to take into account the fact that we have different signs. So now when we write out our energy conservation equation, we have K initial plus UG initial plus the work done is K final plus UG final. Now we need to be careful when we write initial and final. This is actually delta U grav, and the actual equation is just U grav equals mgy. So this will be y initial on this side, this will be y final on that side. So it turns out that in general, we have that delta U is equal to negative the work done by an internal force. So if we're defining our system like this, the internal force is the force of gravity on the ball. So if you calculate the work done by that force, in this case the work internal is equal to negative mg delta y. Negative signs cancel. Mg delta y is the work. That's also our delta U. And this is true with any force. If we can calculate the work done by the force, then we have a way of turning it into a potential energy. Now, this only works for certain types of forces. These are called conservative forces. And an example are spring forces, gravitational forces, electrostatic forces. Friction forces do not have a potential energy function associated with them. One way to think of it is that as the object moves in this direction, it speeds up. But if we were to throw the ball up, as it moved up, it would be slowed down by that gravitational force. However, with a frictional force, imagine that we have a block sliding on the table. If the block slides in this direction, the friction force will cause it to slow down. However, if the block slides in the opposite direction, it's going to slow down again. So the fact that we can use a potential energy associated with a force depends on the fact that that force has a constant direction associated with it. In other words, the direction doesn't depend on which way the object is moving.